Thank you so much, Olivier. Thanks for having me here. It's my pleasure to present this work, which is very new. So it's not even finished, but I'm very excited about it, and I'm excited to share it with you all. Okay, so today I will talk about a whole new problem that it's not studied very much in the area of operations research and optimization. And there's a lot of new vocabulary, so I will walk you through those first. And then afterwards, we'll come back to our own world and talk about large-scale optimization methods to attack this problem. Okay, so first, we'll have quite a bit of time on getting to know this area, the language, the jargon. Afterwards, we'll see how what is the problem exactly there, how we can solve it, and then that would we'll continue the talk with a little bit of preliminary results and observations. Okay, so the topic that we're going to talk about today is called description logic. And this is a family of formal knowledge representation languages. So in the area of semantic web, we'll see what that is. The goal is to make the knowledge that is available on web in a structured way such that the machines can understand it, the computers can understand it, and also can extract knowledge from it. So far what we have on web is structured data, but this structured data, using the usual ways of storing it, we can't really extract knowledge from it. So for example, there are no inferences using an XML sheet. And because of that, the idea of description logic is to provide a language such that, first of all, it's compatible with whatever we have on the web. And second of all, if we present our data and our knowledge using this language, it is understandable for the machine, and the machines can, using some reasoning algorithm, extract some knowledge from it. So we'll see what these things mean, but what do I mean by reasoning here? What is it, this knowledge extraction? That would be checking whether a set of axioms, a set of assumptions, a set of data that is given to us, it's satisfiable, so they're consistent. Doing some sort of classification there. This particular concept, this particular class belongs to this larger class. And also these reasoning algorithms are able to answer queries as well. So these description logic languages, they provide us with a foundation for implementing ontologies, and they are the foundation of what we call semantic web. What are those things? So ontology is a sort of formal representation of knowledge, where we use things called concepts. You can think of them as like classes in an object-oriented language, for example, and relationships, which are sort of functions on these concepts. So ontologies are our way of formally representing this knowledge. And what is semantic web? This would be the idea that we want to extend the current web so that it provides meaning to what we have, this knowledge representations that we have through ontologies, and like being able to reason about them. So for all of these things, naturally, in order to so that these machines be able to talk to each other, these machines need to be able to understand the meaning of the data that we are giving them. Naturally, they need a language. And what is that language? We call it OWL, Web Ontology Language. This is a language that we use for writing ontologies. And these OWLs, they use description logic in order to understand what is written in the ontologies. So we have a lot of different description logic languages. Some of them support some semantics, some of them don't. Some of them support some axioms, some of them don't. And you'll see some examples, some very small toy examples. What are these things? But the good thing is all of these new languages, they are all compatible with what we already have on the internet. They are compatible with HTTP, with XML, with HTML, so whatever protocol, and also languages that we already have on internet, they are compatible with OWL. So when we are able to write an ontology using OWL, when we are able to represent our knowledge and data using OWL, we are extending our current web. So we're not losing anything, we're gaining some knowledge extraction methods. Okay, and then description logic gives us the theoretical foundation for reasoning about these ontologies. So semantic web, in a semantic web, the ideal is that we have data, but it's not just structured like in an XML file. It's not just structured, but it's also meaningful for humans and machines, and it's machine readable. So why not just the data models that we already have, like XML, RDF? XML has syntax, but it doesn't have the semantics that we're looking for. We'll see some of these semantics later on, and we'll see that a lot of existing languages, they didn't support it. RDF, another data model. This one has the semantics, some basic semantic, but no reasoning. So it can't do the classification, it can't do knowledge extraction from the existing model, although it understands it to some extent. But LDL, it provides this powerful tool for us. It it has a very formal syntax. So all of the humans that read it, all of the machines that read it, they already know what to expect. So they can design their own functions, their own reasoners, whatever, using this particular standard language that is provided by the W3 consortium. It has a very semantic, so it supports a lot of axioms, a lot of operators that RDF doesn't, and also it has the capability to do reasoning in the sense of classification, answering queries, and checking satisfiability. So let's see one very small example so that all these very vague things that I said, they are put into context. So now I want to consider a domain, a university. So this is my application domain. Now I want to write an ontology for a university. I want to represent the knowledge of the knowledge that I have about a university using an ontology. So how can I do that? First, I introduced these entities called professors, students, and courses. Of course, we have all other things, but for now, let's start simple. So I introduced these things. And for these concepts, these general concepts, like a professor or a student, I have exactly this term that is called concept. So an ontology is built on the notion of a concept that represents special subclasses of the domain that we are talking about. So in a university, the knowledge that we have about a university includes subclasses of this domain as professors, subclasses of this domain as students, subclasses of this domain as courses. We have some other stuff as well, like full-time students, part-time students. And as you can see, some of these relationships, they can overlap, some of them can subsume the others. So there's no really a predefined condition on them, but we can build these relationships later. And that's what makes this powerful because, for example, RDF or XML or the other existing data models on web, they couldn't do it. So in an ontology, first, we have concepts. Second, we have roles. Roles or relationships, these are functions that relate our concepts together. So we have these functions like teachers, professor, a course. So this tells us that the domain of these function teaches is professor, and the range of this function is course. This is the standard way of writing it. And another function that I'm defining here is enrolled. The domain of this function, enrolled, is a student, and the range is a course. And in an ontology, we also have axioms. Axioms are relationships between these concepts using different operators and also roles. So for example, I want to say something very obvious. Every full-time student is a student. Every part-time student is a student. As you see, when we are able to write these in a way that machine understands them, then it can extract knowledge from it. So we'll see what does that mean, this extracting knowledge. So I want to represent these things using the language OWL. I want to represent every full-time student is a student, and I want to represent every part-time student is a student. So that would be like this. Full-time student is subsumed by student. So it's, as you see, it's exactly like a subset, but well, because the meaning is not exactly the same, we're using this square subset operator. And the part-time student is a student. Now a machine understands this. Now it understands that this class, this concept belongs to another concept. Another thing, a student is either full-time student or part-time student. They cannot be both. So now I can relate these two using another operator, the disjunction operator and also the conjunction operator. So a student belongs to the union of full-time student and part-time student. And there is no conjunction, and the full-time student and part-time student, they are disjunct. Here, this symbol, this is the nothing symbol. So this is a special concept that is a subclass of all other concepts. And it, as the name suggests, it doesn't have any members in it. Another type of information that we can represent using this description logic languages in an ontology are these restrictions, number restrictions. So this is where we will come into play as optimization people. So here I have every full-time student is enrolled in at least 3 courses. That's one of our rules at, I should say, one of our programs, the master program. If you want to have a full-time status, you need to be enrolled in 3 courses. So I can now represent this in a way that machine understands it. And in this standard language that is represented like this, this whole concept of full-time student is subsumed by this anonymous concept that I have created here. Everyone that is enrolled in 3 courses. So at least 3 courses. And I'm using this notion of this operator of greater than equal to in order to represent this cardinality restriction on the number that is required, the number of courses that is required, so that a full-time student is, so the student becomes a full-time student. And we have sort of a negation of that. A part-time student is enrolled in at most 2 courses. Again, I can represent that with this subsumption relationship and this cardinality restriction on the number of the courses, at most 2 courses that a part-time student has. We have a lot of type of axioms that can be represented using this OWL language. For example, I want to represent this existential relationship. So for every course, there exists some professor teaching it. And I can represent it with this subsumption relationship here and say that there exists, there exists a professor, and this is an inverse operator, so that this inverse of teaching would be something like taught by a professor. So here what I wanted to show you was that this standard language, it has these things, this subsumption, this cardinality restriction. So these things, and using these operators, these meanings, it can represent knowledge, it can understand it, and afterwards reason about it. So in this word of description logic, they have, for example, a software full of reasoners, different ways of reasoning. And in these reasoners, we can represent this, our concepts like this. So everybody is a subclass of this general concept called thing. And we have this course, professor, student, and full-time student and part-time student. There are subclasses of student, and this is the knowledge graph. This is the knowledge graph of this our simple ontology. As you can see here in the root node, we have the thing. So everybody, everything in our application domain, in our university world. And then we're saying it's a professor or a course or a student. And then we have these two part-time and full-time students. And these dashed lines, they represent our roles, our relationships. And in order to represent the rest of the, sorry, I did something here. Okay. In order to represent the rest of the knowledge, as you can see, just the knowledge graph is not enough. So we can't see like, we can't say I can use all the other ways of extracting knowledge just using a knowledge graph, because we have this type of information that they cannot be represented using just a knowledge graph. So these type of subsumption or these cardinality restrictions, the cardinality restrictions somehow maybe, but all the other things, the conjunction, disjunction, they cannot be represented with a knowledge graph. And even with this very simple ontology, we can see that if we have something that can find information, that can extract knowledge from our data model, we are already ahead of all the knowledge graphs that exist. So I kept saying that we can extract knowledge, we can reason using this description logic. So let's see what that is. We call this inference. So we can infer new knowledge from our data models, and this is our reasoning. So for example, if to our simple ontology, I add these new concepts. A PhD student, naturally a PhD student is also a student, so I add this axiom as well. And I also add, I wrote seminar twice, so I also add another concept, seminar, and I add this axiom for it. So a seminar at our department, for example, a seminar is something that a PhD student is enrolled in. So, and I'm representing this using our language. We haven't told the reasoner that a seminar is a course. So for us humans, this is obvious. So if the student, the PhD student, which is a student, is enrolled in something, that thing is a course. For us, this is obvious. For a machine, this is not obvious unless we tell them, or there is an algorithm that can infer this as a knowledge. So we haven't told the reasoner, this system, our ontology, that a seminar is a course, but we expect it to understand it. How it can understand it? By implementation of an algorithm behind it. And that's the whole subject of this talk. How we can tell a reasoner to understand this hidden knowledge that for us humans is obvious, but for a machine, for a computer, it's not if we don't tell it. So, and so far, for example, RDF or definitely XML or other data models, they can't understand these things. Like whatever we tell them, they understand. Whatever we don't, and it's hidden via transitive relationships or subsumptions, these things. They don't understand that they can't infer it themselves. So let's go back to this software that I told you. Now I added this Seminar. I didn't tell the reasoner that Seminar is a course, so I just added it as another concept. But I said to the reasoner that this Seminar is this thing. It's very obvious for us. It's very obvious that if a PhD student is enrolled in this thing, then this thing should be a Seminar. But data models don't understand it. But if I ask the reasoner to, okay, reason about this whole thing, this whole data model that I gave you, now it understands that a Seminar is a course. This is huge because in a much larger scale, with all the data that we have these days, it gives the capability to reasoners to understand these things. So if I, for example, give the information about the genome of some species to a reasoner, and I want to understand, okay, what class exactly this thing falls into, then a reasoner can help me here. Then a semantic web will understand what I'm looking for. But using the existing data models, this was not possible. So how does the reasoner, how our reasoner was able to understand it? Using an algorithm behind it. These softwares, they have so far, I think, 10 reasoners that are installed on them, but they're not very good. For some tasks, they are good, but overall, they are not very good, especially when it comes to cardinality restrictions. And that's what we want to help them with. So, and as you can see, the reasoner can even provide us justifications why it was able to tell us that a Seminar is also a course. So it tells us it's because of these two relationships that it was able to say this thing. So a good algorithm, a correct algorithm should be able to do these things, do the classifications, do the queries, do the satisfiability check. And also it should be correct, meaning that for every question that we ask them, they should be able to justify it for us. We call this soundness and completeness. Okay, so from this part of the introduction, we see that description logic is good because it's first of all expressive. So whatever I showed you on the board, you could read it as humans, and also a machine could read it. And also there's a lot of ways of representing different things that previously were not possible, like this subsumption relationships and like the cardinality restrictions. Decidability, so it means that we can, because these are logic, we can design algorithms for them so that we can reason about them. They can be solved algorithmically. They're concise, they're understandable. Like if you've ever looked at an XML file, you see that there is a lot of stuff going on there that we don't need, and it just takes a lot of time just to read it. So it's very difficult. And also it has formal semantics. So all computers, all humans, all machines, they can write in the same language, pass it on to the World Wide Web, and this gives us this whole new tool that is understandable. So what are the constructors and axioms that one of the most powerful description logic, because I told you description logics are family of languages. One of them is called ALCQ, and this is one of the most powerful ones. It's very complete. And so it supports these type of constructors. It has this general concept called a thing. And the thing would be everything in our domain. This delta I is an interpretation of this model. It has the concept nothing. Believe me, this is something that some other description logics, they don't have. So it's strange. It has the notion of a class. A class is a subset of our domain. Concept assertion. So I can say that this individual A, it belongs to this concept class. So Maryam is a professor. Maryam is an individual, but the notion of a professor is a concept. That would be an assertion. It supports negation. There are other languages that don't. It supports conjunction, disjunction, and subsumption. So these are the main tools that we're going to work with. Regarding the roles and functions, naturally it has the role capability, the role assertion. So I can say that Maryam teaches linear programming. Here, Maryam would be this A, and B would be linear programming, the course. And it has universal restrictions. So I can say that all for everyone in a particular concept, a particular role should exist. So for example, all of our students, they should be registered. That would be a function. At least qualified conditionality restriction, so that would be this, at most. Role hierarchy, we can define two roles that are, one of them is subsumed by the other one, like, for example, teaching is subsumed by task. Both of them are roles, one of them is subsumed by the other one. And also a transitive role, that would be like if A and B have a relationship with each other and B and C have a relationship with each other, then A and C also have a relationship. So now all these things aside, what is the problem that we want to help with? That's the problem of satisfiability. Every other problem in the board of description logic and semantic web can be reduced to a satisfiability problem. And it says, these things that I wrote in my ontology, do they make sense? Is there a reality in the world that can be fit into this particular ontology? And can I find, for every concept in my ontology, can I find an instance? So in other words, I can show it with an example. So consider the full-time student that we mentioned. Let's say I'm adding this particular axiom as well. I'm saying that a professor is not a student. So imagine that my ontology has these two information, these two axioms, and then I'm defining another concept in my ontology that is subsumed by professor, the conjunction of professor and full-time student. The question is this thing, does this thing exist or is it empty? We don't want these to be empty. A lot of things don't make sense if this is empty, if a concept in my ontology is empty. So no, this ontology, if I have these two phrases there and I use this third one as a concept, then this ontology is not satisfiable. That's the question that we want to answer. We want to see whether all of the concepts in our ontology, they make sense. There is no conflict between the axioms that we have in our ontology. For a lot of axioms in an ontology and a lot of relationships, these are already taken care of. The issue is with those qualified cardinality restrictions. So qualified cardinality restrictions, in the long history of researchers trying to make these ontologies and semantic web work, these qualified cardinality restrictions have presented the most challenge. And there exist, in general, two ways of trying to incorporate them into this knowledge extraction algorithms that people write. So one of them are Tableau algorithms, and they're very funny. So in Tableau algorithms, they try to reason about these axioms one by one. And when it comes to QCRs, qualified cardinality restrictions, first, they try to satisfy all of the at most restrictions, at least restrictions, and then they get to at most restrictions, they try to merge a lot of those individuals that they found. And if at the end they reach to a conflict, they announce that, okay, this thing is not satisfiable. And it's not possible to find an instance in reality that would fit into this ontology. So for example, for consider this axiom, a person is someone that has two child that are students, something. So they, in order to show that this is, in order to reason about this thing and understand it, first they say, okay, A is a person, Maryam is a person, and then they introduce two other things. So somebody B1 and B2, and they say, okay, so now I say A and B1 and A and B2, they have this relationship. So first, they try to find all these individuals for all of the at least restrictions, but then we have at most restrictions too. So they have to, in a lot of these cases, they can't keep introducing these people because in some of the other axioms, they might become, we might find some conflicts, so they have to merge them. And this is a repetitive and iterative way. And at the end, if they find an issue, then they announce that this ontology is not satisfiable. Naturally, this is very difficult. As the number of the QCRs increases, they can't handle this because it just explodes. So there's another way of looking at these problems, and that's looking at them as a feasibility problem, the way that we do, because all we do is dealing with less than equal to and greater than equal to constraints in our optimization models, right? So about 8 years ago, I got involved into a project like this where we tried to translate this description logic models into optimization models because we're very good at dealing with exactly this problem that they have, right? So there, in a sort of hybrid way, I was the optimization person, so I tried to do this translation and then afterwards try to solve them just for these QCRs. And then for the rest of the ontology, there were the DL people, logic people that they took care of them. But the way that was handled was everything was being taken care of using this Tableau algorithms. Just the QCRs were being taken care of using optimization methods. So there were huge amount of improvement, but still, yeah, that nature of iteratively going through every axiom, it didn't look good to me. So the idea for the way that I want to handle this problem in this project is to reduce the whole thing into an optimization model, because if we can do that, then the problem becomes just the largest scale optimization problem that we need to find whether it's feasible or not. So this requires translation of everything from description logic to equalities, equality constraints, inequality constraints, the way that we model our problems. So I just show the idea using an example. In this simple example, I have these 4 restrictions. I have 3 roles, R, T, and S. And these 3 roles, there's like greater than equal to 3R, less than equal to 2T. So I have these 4 restrictions, some of them greater than equal to, some of them less than equal to. The way that this translation works is we call it atomic decomposition. I should not use the same S. We call it atomic decomposition of this set. And it goes like this. I consider everyone that is involved in a relationship R like this, like a set. Everyone that is in a relationship via T, like this blue set, and everyone that is in a relationship via role S, like this yellow set. And then naturally, some people might be in a relationship via R, some people might be in a relationship via T. So there might be some overlaps between these sets as well. There is nothing that restricts us from it yet. So as you can see here, as a result of these three sets that we defined, 4 people that are in relationships, we got 7 partitions. One partition is just R, this part, one partition is T, one partition is S, and another partition is these 2, R and T, so this part. So for every part of this 3 sets, we have a partition. Then I define this variable VISITIR for each partition. So V001 would be partition 1 because there is no S, there is no T, there's just R. So every one of these ISITIRs, they represent the presence of this role in that particular partition, that particular subset. So now I have this decision variable, and now magically this S is reduced to a bunch of inequalities. So now I'm saying all these decision variables that I defined, and they have R, all of them, the summation of all of them should be greater than or equal to 3, as is here, the first one. So that's exactly what we have here in the QCR that was here. So we were saying that like this individual, whatever that is, it should be like greater than or equal to 3R. There should be, I should be able to find 3 instances that are in relationship with R. And that's what I'm doing here. I'm saying the number of members that have R in them. So that's why all of these have this index 1 here. It should be at least 3. The same thing for the second one, for 2T. So here, all of the second indices, they are 1. So the summation of all the partitions that have R in them, it should be at most 2. So I should find at most 2 instances, 2 individuals that are in relationship via the role T. So this way, we're able to translate these qualified cardinality restrictions to inequalities. When we do that, we are back to our own beautiful world, and we can understand these things, because it took me a year to understand just what they are talking about. The jargon and everything is very difficult. So now we have just the feasibility problem, right? This is the summation of those V variables. So for if I have this set R of roles like this, for every role, I can define this restriction, if it exists, using those decision variables that tell me whether this particular role exists in that particular subpartition or not. So now the summation of these V variables should be less than or equal to the bounds that are given as cardinality restrictions. And the objective function here, I have defined the numbers because I want the minimal number of individuals that satisfy these conditions, because at the end we want the explicitly entailed instances. It's not important. What's important is this, that we can write those QCRs in this compact form, in this optimization form. But how many partitions do we have? As you saw, the number of partitions, so here, I defined for every role that I had 3 roles, 4 restrictions, but just 3 roles. So I had 3 roles, and then I was looking for the subsets of them, right? So how many partitions do we have? That would be the power set of the set of roles. So that's huge. This means that here I have a huge number of variables. So yeah, and also there's this was just QCR. There were not the other axioms to be to consider. How can we solve it? We know how can we solve it. We are going to use the extended formulation and then afterwards use a branch and price framework to solve this problem. So in order to not repeat greater than equal to, less than equal to, I'm using this notion of a bow tie. So that would be either less than equal to or greater than equal to. I define a mapping here. I say, okay, for every restriction, I'm going to define a subrole. And then I'm going to define this set as SQ. And what is this set? It's these mappings. So all the subroles that I've defined, think of subrole as just one of those sets that we want to, at the end, get the intersection of. Yeah, SQ here is the set of those subroles, as well as the set of all the concepts that are involved in those QCRs, and the set thing and the set nothing. Then I define this, the power set of SQ. That's what we defined every one of those decision variables for. And now, because I want to define extended formulation, right? So I'm going to define this thing that I call a partition configuration. This is what my pricing problem is going to find. So a partition configuration here represents a partition. So I'm not going to consider all of those partitions in the power set all at the same time. I'm going to implicitly enumerate them. I'm going to gradually build them as I go, as needed. So for every one of these subroles that I set here, I'm going to define this parameter that tells me whether that subrole exists in this partition. So for example, here, what did we have? Here for R, the parameter ARP for the first partition would tell me that it exists. But for the other 2, it would tell me that it doesn't exist. So that would be the characterization. That's how I characterize these partitions. And also, I'm defining a cost for every one of these partitions. I'm saying that I'm defining this cost as the number of concepts that exist in this partition. Why? Because I want to find the minimal solution, so the explicitly entailed concepts. If I do that, the extended formulation can be written like this. I'm defining XP as an integer decision variable that tells me how many times this partition is found. So that every one of these XPs would correspond to one of those V decision variables. And then I want to minimize the number of, as I mentioned, I want to minimize the number of concepts that I find at the end because I want to find a minimal solution. And then for greater than or equal to restrictions, I just write it like this. So the summation of all those decision variables that include this role R prime, that should be greater than equal to the cardinality restriction that was given to us as this greater than equal to QCR, and the same thing for less than equal to QCRs. So we know how to solve this. This is a branch and price. We don't know, but we have an idea. So this we are going to solve with a branch and price framework. So we are not going to work with all of the sets, all of the partitions in P. We are going to gradually create them using a pricing problem. How are we generating them? So first of all, this was an integer programming problem, right? So the first thing I do is I relax it. I first write the column generation formulation for it. So I relax it. and I define these two dual vectors for these two constraints. So pi for the first one and omega for the second ones. I defined two because I want to create this partition, right? So the parameters that characterize the partition now become my decision variables. This AR prime, which was the parameter that told us whether a particular role exists in my partition, now it's my decision variable. Also, I'm defining BC, which tells me whether this particular concept C exists in my partition or not. And if I do that, then my pricing problem becomes like this. I write the reduced cost as we do. And then for every one of the roles that is involved in a QCR, the presence of that role would mean that C exists as well. So this means that if AR prime is equal to 1, then, but if it's a less than equal to constraint, then BC should be equal to 1 as well. And the other way, if it's a greater than equal to constraint, then if BC is equal to 1, then AR1 should be equal to 1. So this logical relationship between the two. Everything is a member of the thing, as we saw in that software. So whenever BC becomes 1, B of theta becomes 1 as well. B of nothing should be always 0. Then we have this all other axioms, which I will briefly show. I'm running out of time. And the fact that, well, all of these decision variables, they're binary. So how do I map these things? I'm gonna consider some of these axioms as basic and then reduce all the other axioms because we had a lot, right? So I consider some of them as basic and then reduce all the other ones to them. We have QCRs. We know how they are being handled in the master problem. The subsumption, because now I'm dealing with binary decision variables. So if I have BA, naturally I will have BB too. It's a subsumption relationship. So if I'm a full-time student, then I'm a student too. Because of that, if BA is 1, then BB should be equal to 1 as well. I have binary subsumption. So the conjunction of these two, the overlap of these two would give me C. We know how to model that in integer programming. So we do that. We also have this disjointness relationship that we can model and the relation and the negation. So if I'm C, I cannot be not C. So between BC and not C, only one of them is equal to 1. All the other axioms, we can show that they can be reduced to these basic ones as well as the QCRs. So imagine if I have an ontology, I begin by normalizing it. So I bring everything down to QCRs and those basic axioms. And I can show that all the other axioms, we can do that for them. So for example, consider this A is subsumed by disjunction of B and C. If I write the negation of this whole thing, the contrapositive of this whole thing, that would give me the negation of B in conjunction with negation of C is subsumed by negation of A. So writing the contrapositive of this. And this brings us back to the binary subsumption case, one of the basic axioms. And for all the others is the same. So now we know how to solve the relaxation of this problem. I can first of all pass this on to branch and price framework, and in our implementation, we have the implementation, but the funny thing is we can't test it. We can't test the integrality because for all the cases that, all the ontologies that we've tested, including the real ones and the synthetic ones, the optimal solution that the column generation has returned for us has been integral. So, and that's why I included this as a conjecture because I wasn't able to prove that the polyhedron is integral yet. So yeah, using like totally modularity and the other sufficient conditions that we know, I wasn't able to prove it. Maybe someday we find an example that doesn't fit this. But yeah, so far we have this conjecture that the polyhedron is integral and we don't need the branch and bound part. But it's there. So if someday we need it, we can just branch on the binary variables that represent every partition. So some preliminary experiments. We compared our reasoner using these measure reasoners, Hermite, conclude, racer. So these things that are inside that software that I briefly showed some screenshots. And we use this benchmark ontologies. This one is variations of a real ontology that represents the Canadian Parliament. It includes like the PMs and everyone for every one of the provinces. It has a lot of QCR relationships. So even this many for those Tableau algorithms is a lot because they do it repeatedly. These two are synthetic, therefore checking whether something is unsatisfiable. And these two are also variations of a real ontology on genomics. And the early observations for the Canadian Parliament ones, only us and Racer were able to do the classifications and verify that all of these concepts, they are satisfiable within 1,000 seconds. For the second benchmark, the synthetic one, so as you see, a lot of them, they time out. But we were good. Racer was good too. So give them credit. Racer was good too. Racer is like the best reasoner that exists, and it also has a sort of ILP component, but not the way that we consider. And for the genomic ones, this one has a lot of QCRs, but this concepts that are defined on, they don't have any relationship between them. So it's an easy case. All of the reasoners work well on them, including us, except Racer this time. So overall, we're good. And yeah, so this is, as I mentioned at the beginning of the talk, it's an ongoing work. And so far, whatever I had, it was just proof of concept. And it'd be nice to have reasoner that the way that we're doing it, it's all ILP because we have a lot of enhancement algorithms and algorithms that I presented here to solve this large models is just like our basic column generation. And we haven't used any of the new advancements. For us, the bottleneck so far is the normalization of those non-basic axioms, which is taking longer than we want, but technically it shouldn't take long. So we should find that out, what's going on, and the conjecture, because if we prove it, then it would simplify the implementation for future and also presentation to non-OR communities. And thank you so much for listening.